Okay, so hello everyone. We keep on talking about ZKVM. So this talk is going to be not on formal verification. It's going to be a talk about strong notion of knowledge soundness for ZKVM. So a bit more on the theory side, respect what we've seen in the previous talk. This is a joint work with Matteo and with my student Luigi. So I'm going to be a bit redundant here. We've seen these things already again and again during these days, but let me repeat for all of the people that were sleeping until now. So proof of program execution, there is a verifier and there is a prover. The prover wants to prove that a program P on a public input X and a private input W run and you output Y. And he wants to prove it to the verifier, and there are many ways to do that. Among the most efficient way to do that is to just send a ZK SNARK that the proof indeed that the program indeed correctly computed Y on input X and W. ZK SNARKs are zero knowledge, are non-interactive, are succinct, are argument of knowledge, and that's kind of the solution for this problem, one of the solutions for this problem. So again, I'm going to be redundant again. The classical approach would have been to take your program that you want to prove the execution of. You can compile this program in an intermediate representation or a SNARK-friendly representation. Let's say R1CS, Plonkish, CCS. And then you would run your ZK SNARK on this representation of this program and program P on input X. Let's forget for now about the private input W, output Y, so you use your SNARK to prove that. The ZKVM approach is instead of compiling a program by program, just compile a CPU. Theoretically, let's call it like a universal circuit, and this universal circuit takes in input both the program and input for the program, and so we get again from the CPU, we go through the intermediate representation, the SNARK-friendly representation of the CPU, and then we have this universal program, and at ZKVM is just a SNARK that can prove that the universal circuit on input, the program P, that now you've written on your nice and easy to work with language on input X, output Y. Why we want to do that, I shouldn't insist on why this is a nice way to approach this problem. Some of the reason is for formal verification, so the idea is that you should focus on the formal verification of the circuit and that's it, and then you're good. Apparently that's not true in practice, but in theory should it. And we can reuse existing languages and tooling and so on. So this is a good approach. So many applications of ZKVM, generic use cases are like proof of solvency, image provenance, content moderation, fancy t-shirt, and so on. The killer application are for blockchain-related applications. I can mention private transaction, private smart contract, ZK rollup. And when we focus on blockchain-related application, we see that we want to send our proof on the blockchain. So now the theoretical question will be, can an adversary, by looking at all proof in the blockchain, somehow break the knowledge soundness of the ZKVM? So this is the question that we're trying to answer in this work. So let me repeat it again. So what we want to fight against are the so-called malleability attack. In this malleability attack, there is an adversary that gets in input proof, so it takes it from the blockchain, and the property that we want to analyze is the fact that an adversary with extra information, for example, a proof, shouldn't be able to modify this proof, change this proof in a way that it can prove a statement for which he doesn't know the witness. So we should be able to extract this proof by star. Of course, the only trivial attack will be the copy-paste attack. This is unevitable. It turns out that these kind of attacks are not ruled out by zero knowledge, neither by knowledge soundness. We need a stronger notion of knowledge soundness. And let me talk a little bit about this stronger notion of knowledge soundness that is needed. So the stronger notion of knowledge soundness that imply non-malleability for zero knowledge SNARKs is the so-called simulation extractability notion. So what is this simulation extractability notion? It's basically the same image that you see before. Now we have an adversary that has oracle access to the simulator, and the adversary is playing the knowledge soundness game, but in the presence of a simulated proof. And again, here he has to forge a proof for a new statement, meaning that to avoid the trivial copy-paste attack. So the adversary interacts with the zero knowledge simulator and then forge a proof. We need to consider ZKVM that are indeed zero knowledge, and as Alexander mentioned in his talk, ZK in ZKVM is kind of a lie, but in this talk, ZK in ZKVM is true. So let's look at the complexity of ZKVM. We've seen it in the previous talk that ZKVM are very hard and very complex tool, because the idea is that we need to handle a universal circuit, and this universal circuit we want to fill it up with a lot of instructions. Let's say, for example, the instruction set of RISC-V have more than 50 operations. So we will need a circuit that has a giant switch with all the possible cases. And as we've seen in the previous talk, it's not only that. We need to handle not only the instruction being executed, we also need to handle the fact that, a witness for the ZKVM is just a sequence of snapshots of this virtual machine. And we need to be sure that between step 1 and step 2, there is consistency in this snapshot. So we need to check that the memory is consistent through the entire computation, that the fetch, decode operation are consistent during the execution. So we need to handle RAM, program counter, registers, and so on. Okay, so we wanted to analyze the simulation extractability of ZKVM. First thing that we notice is that almost all the ZKVM follow a modular design. This is just natural, just the correct way to do that is the natural way to do that. We settle down for Jolt, which is a ZKVM based on the lookup singularity. And actually what we propose as a ZKVM that is non-malleable is something that we call a Joltish, which is inspired by Jolt. It's not quite Jolt for some technical reason, including zero knowledge. And these ZKVM are, broadly speaking, divided in two big components. So they are modular and they are divided in a big SNARK that check memory and check fetch and decode and so on. And then there is a big SNARK that is for the CPU instruction. So the fact that the XOR was well executed, the AND was well executed, and so on. So this is kind of the ZKVM that I'm considering right now. So the goal of this work was to understand what are the conditions to assess the non-malleability of what we call Joltish. And let's look into this question. So now, in theory, this question can be generalized just a little bit. So instead of the previous question, let's consider the question, what are the conditions for non-malleability of modular composition of SNARKs? This is a very natural question. And it turns out that trivial composition doesn't work. That seems like easy to show. The fact that if you have SNARK number 1 that is non-malleable, SNARK number 2 is non-malleable, you just concatenate these two proofs together. What you obtain is not something that is non-malleable. And the idea is that there are this so-called copy-paste attack. Basically, what I can do is that just to simulate one of the proof and then prove a correct proof for the second one. And this is going to be like I'm proving something that I don't completely know. Okay. Here the problem is that there is no glue between SNARK 1 and SNARK 2. So we need to kind of glue them together somehow. And the way to glue things together is by using a commit and prove relationship. So a commit and prove relationship contains in this instance a value X, but also a commitment C. And the kind of statement that it proves is that a predicate P on X and W is equal to 1, and that the witness W is indeed committed in C. Now we can define the conjunction between the commit and prove relationship, which is like the end between two predicates, such that the witness is committed on a commitment C, and this commitment is this witness is shared between the two instances. Okay, what about the non-malleability now of the compiler in which we attach together these two proofs? We give two different compositions, and we show these compositions are indeed non-malleable. Okay, so let's see the first composition. The first composition is the natural one. We have so our prover for the conjunction would, on input x1, x2, and w, what he will do is to commit to w. Then he would use the first SNARK to prove the relation number 1, the second SNARK to prove the relation number 2. Now, if the two building blocks are trapdoorless, zero knowledge, and simulation extractable, meaning non-malleable, then the output is going to be simulation extractable and trapdoor zero knowledge. Here I'm not talking you about trapdoorless zero knowledge, it's just a restricted form of zero knowledge, just for technical reason. Okay, it's a notion quite used in the case of random oracle-based zero knowledge schemes. Okay, this seems like natural and easy to prove. Next construction is just incrementally a bit more difficult, not much than that. So what if instead of using a simulation extractable scheme for the SNARK number 2, we use a signature of knowledge? The construction works as follows. We commit to the witness. We prove using the SNARK number 1 the first part of the relationship. We prove using SNARK number 2 the second part of the relationship. And since the second SNARK is also a signature of knowledge, what we can do is we can sign arbitrary message. And what we're going to sign, the proof of the SNARK number 1 using the SNARK number 2. So pi2 is a proof, which is also a signature of knowledge for pi1. So we attach together these two proofs. And now here, it turns out that we can relax the property, the security property required by the SNARK number 1. And it turns out that this thing is quite useful for us. So the theorem say that if the SNARK number 1 is witness indistinguishable, knowledge soundness, and efficient witness computable, and the SNARK number 2 is trapdoor at zero knowledge and a signature of knowledge, then the construction, the compiled SNARK is simulation extractable. Here, maybe the only notion that you might not be aware of is this efficient witness computability. And this efficient witness compatibility is basically what allows us to do the trick. So the idea of efficient witness computability is that if I can sample the commitment myself, then it's easy to find a witness W for the value x1. Basically, the relationship is almost in P, beside the commitment part. Okay. Here, a very, very easy sketch of why this is secure. So the idea is that the zero knowledge simulator for the conjunction can just compute an honest proof pi1, and it needs to simulate the proof for pi2. It can compute an honest proof pi1 because of the efficient witness computability property. And the reduction to the knowledge soundness on SNARK 1, it's easy because now you don't have to handle the simulator. So we just reduce the knowledge soundness. And now it turns out that this scheme could be completely malleable. So what can we do to make sure that any malleability attack is kind of avoided? We sign the proof pi1 with the simulation, the signature of knowledge pi2. In this way, every time that an attacker tries to modify pi1, he has to modify also pi2, but pi2 is simulation extractable, so he will have to forge a valid witness. We could be able to extract a valid witness. So that's the idea of our compiler. Good. So now let's go back to the ZKVM. Let me recall again what is the architecture of a ZKVM, specifically of our Joltish ZKVM. So these two pieces, SNARK for memory checking, fetch and decode, SNARK for CPU instruction. The witness is a trace, which is a snapshot, many snapshots, one after the other of the virtual machine. And the idea here is to use the second compiler, the one in which one of the schemes just have to be knowledge sound. And so we assume the SNARK for memory checking, fetch, and decode, which is basically also the most complicated part of this construction. We just assume it to be knowledge sound. And we need to assume a simulation extractable ZK SNARK for CPU instruction. And this is going to work. And I'm going to tell you why this is going to work. And basically, the idea is that the SNARK number one, it is efficiently witness computable. So the idea is that, for example, let's define this simulator for for Joltish. Let's suppose that we feed the simulator with a program P, an input X and Y, and what the prover should do, that P of X is equal to Y over a RISC-V architecture. What the simulator, we can feed the simulator with this P, X, and Y. Let's assume that this is a wrong statement, so that the P of X is equal to a value Y prime, which is different than Y. And the simulator should prove that the P of X is equal to Y on a RISC-V architecture, anyway. So the trick here is that we can hack the instruction set in such a way that by hacking this instruction set, we end up with a program that if we run the program on this hacked instruction set, we actually obtain that P of X is equal to Y. Now we run this program, we obtain a trace of execution of this program, and it turns out that this execution trace is a good trace for the first SNARK, because we actually executed the program as it is, but on a hacked instruction set. This witness is not going to be a valid witness for the SNARK number 2, but here it's fine because we can use our simulator, and our simulator is a simulation extractable scheme, so it's fine to prove a fake statement for this part of the scheme. Okay. So let's continue non-malleability of Joltish. So this is basically one part of the result that we present in this paper. And so now we want to talk about the lookup singularity. So the idea of ZKVM based on the lookup singularity is the fact that we substitute the SNARK for execution of instruction using a lookup argument. So what we need really to fill the hole in this construction is to have a simulation extractable lookup argument. Okay. So what is a lookup argument? A lookup argument is a SNARK that allows to prove that a committed vector f is a subvector of a big table T. Here f is much smaller than T. Here what we want for a lookup argument is that the prover complexity is only proportional to f, or I mean, yeah, it might be proportional to T, but in a way that is like succinct. Lookup arguments right now can handle very big table, as big as the truth table of a RISC-V instruction set. So this is the idea behind Jolt in some sense. And what is the lookup argument behind Jolt? It's lasso. So the second part of this paper is really about proving the simulation extractability of lasso. And to prove simulation extractability of lasso, we actually need to first define a zero knowledge version of lasso. And then we prove simulation extractability for zero knowledge lasso using a framework based by this work by Faust et al., which is basically proving trapdoor zero knowledge, unique response, special soundness, and this is imply simulation extractability. we extend and improve over a work by DAO and Grab. This is because Lasso is based on Spartan, and Spartan was already proved simulation extractable in that work. And actually, even if I'm just giving one slide to this part of our work, this is indeed where all the mathematical heavy lifting went on. Okay, this is conclude my talk in 20 minutes. So what about future works? So non-malleability, I think an interesting future work would be about the non-malleability of SNARK. Here, looking backward, to prove non-malleability of Joltish, we had to first define a zero-knowledge version of Lasso. So this is because the definition, that's definition what they say, you need to have a simulator to formally prove simulation extractability. So what about non-malleability without resorting to simulation extractability? Are there some notion that can capture that? Another thing, and the part of the talk that I emphasized the most was about composition. And here I looked at composition, we looked at composition of commit and proof SNARK, but another tool that is very amenable to composition, which is basically invented for composition, is reduction of knowledge. So what about the non-malleability of reduction of knowledge? Can we have tricks like what I explained before, that only one of the two components needs to be simulation extractable, and then you have it. So you put all the complexity on what where you don't know how to prove simulation extractability, but the last component is going to be simulation extractable, and that's going to fix your task. And as well, a natural question is about non-malleability of other lookup arguments. And that concludes my talk.
Sorry to hog the mic a little bit. Can you comment on the sort of the compositionality of strong simulation extractability versus weak simulation extractability? Because I could be wrong, but I think weak simulation extractability composes more naturally because so to summarize, it allows the proofs to be malleated, but they are committing to the instance, the public variables. And a proof for a given instance doesn't help you to generate proofs for a different instance. So my experience with using that notion, for example, in security arguments for Zcash, is that it's just as easy to assume weak SE because you have to handle pasting of proofs anyway. So would it be easier in general for us to just concentrate on weak SE as the basis of composition?
I think it's really application dependent. I mean, I wouldn't say that I wouldn't call it weak simulation extractability and strong.
Weak is slightly misleading because it is actually quite a strong property.
Yeah. Because, I mean, weak simulation extractability, for example, we saw UC security of growth. Growth is randomizable. Randomizability sometimes is kind of a good property that you would like to have. In some other setting, no. When you're using your proof as a token, then in that case, you really want to have strong non-malleability. So maybe the naming weak and strong should be rephrased. I will call it controlled.
Can you give a little more detail about hack the instruction set? What exactly is being done there?
Yeah, I cheat a lot there. So the idea is that so you have your program, and your program has a bunch of instructions, and you can focus on the last extractions that your program has to execute. And now here I'm gonna do just an extraction that instead of the program will say you need to do an add. Now I modify the instruction in the simulator in a way that this instruction instead does a print y. So at the end of this program, this act program will at the end print y, just because I act what was the last instruction that he executed. So I'm just renaming this add to do what I want to do, and now I'm proving a false statement for the lookup. The lookup is looking up for 2 plus 2. You should find 5. Instead, they found a y. Right? And that's just a trick. And I'm proving something false, but I'm proving something false using a simulation extractable lookup argument. So in terms of security, I'm fine. Does it make sense? Thanks.
I didn't understand.
Well,
any other questions? Okay, thank you.